Hi, in this section, section 12.4, we are going to analyze graphs. So all of the tools that we learned in sections 12.1 through 12.3 about maxima and minima, first derivative test, the second derivative test, all of that information we're going to use here in section 12.4. So what you may want to do is review page 951 in your books. And what that does is it summarizes all of the steps that you need to take in order to graph or sketch the graph of a function. Now, notice that here the goal of this section is to use tools from calculus to understand beautiful mathematical curves that you can graph using technology. But here in this section, I'm going to show you how to sketch the graphs by hand. Okay, so for the following examples, I want us to sketch the graph of the given function indicating A, the x and y intercepts, B, the extrema, C, the points of inflection, D, the behavior near singular points. So what does D mean? D means we need to look at the left and the right hand limits as x approaches a singular point. And E, we need to look at the behavior at infinity. So let me move this over and move it up a little bit so we can have room for our example. And let's begin. Now, our function is f of x equals x squared plus 1 over x squared. Now, first things first, part A says we should find the x and y intercepts. So let's do that. So, part A, to find the x-intercept, or intercepts, we must set y equal to 0. Now what's y? Y is this function here. We can call it y instead of f of x. So let's find that. So we have 0 equals x squared plus 1 over x squared. And that means negative 1 over x squared is equal to x squared. All we did was move this term to the left-hand side. And now, if we cross multiply, meaning we write that over 1 and cross multiply here, meaning cross multiply, we get that negative 1 is equal to x squared times x squared, which is x to the 4th. Now what we know here is if we take the 4th root of both sides, then we're going to have, if we're able to take the 4th root of both sides, then we're going to have a negative number here underneath an index that has, underneath a radical that has an even index. So we're going to end up with imaginary numbers, which means there are no real solutions here. So there are no x-intercepts. Okay? Now, in part B, well, we're not done with part A. Part A says the x and the y-intercepts. So in part A, we need to find the y-intercepts. To find the y-intercept, we must set x equal to 0 and solve. So if we set x equals to 0, that means we're finding f of 0. Well, f of 0 is equal to 0 squared plus 1 over 0 squared. Well, what do we know about that? We can't divide by 0. That means this is undefined. So for this particular function, there are no x-intercepts and there are no y-intercepts. Or there is no y-intercept. Okay? Now, in part B. Now, in part B, we want to actually find our extrema. Now, to find your extrema, or our extrema, we need to make sure that we find our derivative first. So let's do that. So now we're in part B. We're finding our extrema. So we need to find our derivative. So in other words, we need to find f prime of x. At this point, you may want to rewrite f of x as x squared plus x to the negative second, because it might make differentiating easier for you. So f prime of x is going to be 2x minus 2x to the negative 2 minus 1, which is negative 3. So rewriting that, we get that as 2x minus 2 over x cubed. That's rewriting it. Now, we want to find our extrema, so we need to find our critical points. So let's set f prime of x equal to 0. That means 2x minus 2 over x cubed is equal to 0, or 2x is equal to 2 over x cubed. Now, same rule as before. Cross multiply. When you cross multiply, you can think of that over 1. And then you get 2x to the 4th equals 2. Or moving up here, we get, dividing both sides by 2 here, we get x to the 4th. We can make that better. X to the 4th equals 1. Now you take the 4th root of both sides. So we have the 4th root of x to the 4th is equal to the 4th root of 1, which means we get x is equal to plus or minus 1. Now we need to figure out if plus or minus 1, if there is a minimum at plus or minus 1 or maximum. Okay, so we're going to use the first derivative test. Remember our number line, you can mark negative 1 and you can mark 1. And just to note that we also find critical points whenever we see when f prime of x is undefined. Note that here, f prime of x is undefined when x is equal to 0, because we cannot divide by 0. But our original function, we've already taken that into consideration. Because 0 cannot be in our domain, that means we're going to have an asymptote of 0. So we don't need to worry about that point necessarily here. Okay, so let's choose a number to the left of negative 1 and the right, okay, to see what happens. Well, if we choose negative 2, we're using the first derivative test, so we're going to substitute that into this particular function, and then that would give us 2 times negative 2 minus 2 over negative 2 quantity cubed. That's equal to negative 4 minus 2 over negative 8. So that's going to be negative 4 plus a 4th, which is going to be negative. Okay, now we also need to check a number to the right of negative 1, but it can't be 0, so it has to be between negative 1 and 0. So let's choose negative 1/2. Okay, so then we plug it into our derivative. We get 2 times negative 1/2 minus 2 divided by negative 1/2 cubed. That's going to give us negative 1 minus 2 divided by negative 1/8. So that's going to be negative 1 plus 2 divided by 1/8 is the same thing as 2 times 8 over 1. Okay, which would give us 16, which means, hey, this is positive. So it changes from negative, your derivative changes from negative to positive at -1, which means we have an absolute minimum. Okay? Now, if we check between -1/2 or -1/2 and 1, if you choose a number there and then you choose a number to the right, you're going to find the same exact thing. It's going to change from negative to positive. I'll leave that for you to do. Remember, what I'm leaving for you to check is to choose a number here between, not between -1/2 and 1. Let me stand corrected. Between 0 and 1. So choose, when you're testing it for yourself, choose 1/2. That's a 1 here. 1/2, and then to the right choose 2. Check it, and you indeed get a negative number and a positive number. So you indeed have a minimum at 1 as well. So that will, all of that tells us that we have an absolute, our function f, using the first derivative test. So let's say by the first, it's an I, derivative test, f has an absolute minimum at -1, something, and 1, something. Now, to figure out what the somethings are, we need to substitute these values, -1 and 1, into our function f. So let's do that. So we're going to substitute those into our function f of x. So whenever you substitute in -1, you get -1 quantity squared, which will give you 1, and then 1 plus 1 gives you 2. So we get 2 here, and whenever you put in 1, we get x squared, or 1 squared, plus 1 over 1, so you get 2 again. So putting all of the information we have so far together on a graph, we're sketching a graph. We know x equals 0 is a vertical asymptote. Okay, so we have our x-axis, we have our y-axis. We know that -1, 2, let's say that's 2, is a minimum, an absolute minimum, and then 1, 2 is an absolute minimum as well. Now, part C says we need to find our points of inflection, which means we need to examine our second derivative and see what happens. Well, in part C, we need to look at our second derivative, f double prime of x. Well, let's remember our first derivative was 2x minus 2x to the negative x. So our second derivative is going to be 2 plus 6x to the -4. In other words, 2 plus 6 over x to the 4. Well, this is never 0. This is never 0. Well, because it's never 0, that means there are no points of inflection. So there are no points of inflection. Okay, now in part D, it says we need to find the behavior near our singular points. Remember, singular points you have when your function is undefined, your singular points of f. Well, we found out that our function was undefined when x was equal to 0. Our function was undefined when x was equal to 0. So that means 0 is a singular point. Okay? So in part D, we have f is undefined or singular we're finding out the behavior near our singular points. Now we're examining. What does that mean? It means we are examining the left and the right hand limits of our function f of x as x approaches 0. So we need to examine that. Separate this, make it a little bit neater. We have math everywhere. Now, what does this give us? Now, this is the limit as x approaches 0 on the right of f of x, remember, is x squared plus 1 over x squared. And as x approaches 0 from the right of x squared, remember x squared. So let me make it a little bit smaller and move it over so you can see what I'm saying. Note that the graph of x squared, x squared, the graph of 1 of x squared, the graph of 1 over x squared. To the left. As x gets closer and closer to 0 from the right hand side, x squared goes to 0. As 1 over x squared gets closer and closer, as x gets closer and closer to 0 from the right hand side, 1 over x squared goes to infinity. So that means we have this is 0 plus infinity, which is infinity. Okay? Now, what is the behavior of our function at infinity? And I'm running out of room. So let's write that below the graph. We're looking at part E. So now we're going to look at the limit of f of x as x approaches infinity. Well, again, what we have to do is look at the limit of f of x. Well, we just said f of x, but now let's write it in. Now let's look at one more example. F of x equals 2x over 5 minus the quantity x minus 1 raised to the 2/5. The book says use technology for x-intercepts. I will give you examples where you're able to do this by hand. So now you should pause the video and go through the same steps A through E as we did in the first example, but do that with this particular function instead. So give it a try. Pause the video, use this as your function, go through steps A through E given on the previous page for this particular example. Okay? Now, you should be back. Hopefully you worked through that. And now what we're going to do is work through it ourselves. Now, if you take a minute, you can graph this function using your calculators, and when you do, you look for the x-intercepts. So look for the points at which your graph crosses the x-axis. So if you do that, then part A will tell you your x-intercepts from the graph. So that's using the graph you use for your calculator. From the graph means that x is approximately, wavy equals approximately 0.9, 1.1, and 3.7. Okay, now your y-intercept, you don't need to use technology for that. So your y-intercept, remember you set x equal to 0. When you set x equal to 0, you get, we're finding f of 0. That would be equal to 0 minus -1 raised to the 2/5, which gives us -1. So our y-intercept is -1. So if you're putting your graph together, so far, you know you have 3 x-intercepts. So one at 0.9, you have another one, so this is 1, but you have an x-intercept here. You have another one at 1.1. You have another one at 3.7. And we know we have now a y-intercept at -1. Okay, so that's what we know. Now in part B, we have to find our extrema, which means we need to find our first derivative. F prime of x is equal to 2/5 minus 2/5 times the quantity x minus 1 raised to the -3/5. Okay, remember you're doing 2/5 minus 1, so that'll give you -3/5. Okay, you can rewrite that as 2/5 minus 2 divided by 5 times x minus 1 raised to the 3/5. Okay, now why did we do that? Because we want to find our critical points. Our critical points. Well, the easiest one is whenever f prime of x is undefined. F prime of x is undefined when, so we look here to find out when our denominator is 0. Well, here it's just a number here though. If x is equal to 1, that makes our denominator 0. So that's how we get x equals 1 is a critical point. And now we also get a critical point whenever we set it being your derivative equal to 0. So f prime of x equals 0 means 2/5 minus 2 over 5 times the quantity x minus 1 to the 3/5 equals 0. Or in other words, 2/5 is equal to 2 over the 5th root, not the 5th root, 5 times the quantity x minus 1 to the 3/5. And now we can cross multiply, and that gives us 10 times the quantity x minus 1 to the 3/5 equals 10. Okay, cross multiplying. Now we divide both sides by 10. That means those 10s go away, and we left with x minus 1, that quantity, raised to the 3/5 equals 1. Now, to eliminate this 3/5 power here, we need to raise both sides to the 5/3. So, next step is raising both sides to the 5/3, because 3/5 times 5/3 is what? 3/5 times 5/3 is 1. So that leaves us with x minus 1 equals 1. Okay? Which means x is going to be equal to 2. So our critical points, we have x equals 1 and x equals 2. Now we need to see whether we have relative extrema, relative max or min, at x equals 1 and x equals 2. So let's do it. We're going to use the first derivative test. Okay? So, using the first derivative test, so notice that we're using this so much. So you should have all of your derivative rules, differentiation rules written down. You should have your derivative test written down as well. So remember, we use our number line. We mark our critical numbers. So we have one at 1. We had another one at 2, our critical points. Okay, and now we need to test values. Values that you can test are 0, 1.5 or 3/2, and then you can also check 3. Okay, I'll go through one with you and you can check the others on your own. We're using the first derivative, remember? So you're taking that value and you're substituting that value in there. Okay, so f prime of 0 is equal to 2/5 minus 2 over 5 times -1, because we put in 0 for x, raised to the 3/5. Well, that's going to give us 2/5 minus 2 divided by, notice that -1 raised to the 3/5 is -1. So this becomes 5 times -1, which would give us -5. So that is 2/5 plus 2/5 is 4/5. But all we care about really is that this gave us a positive number. Now, if you find f prime of 3/2, you should take the time and plug that into your calculators. Once you find that, you're going to find out that you get a negative number. So fill in on your own. Then find f prime of 3. When you find f prime of 3, fill this in on your own as well. You're going to find out that that's going to give you a positive number. So notice that Your derivative changed from positive to negative at 1, which means you have an absolute or relative, not absolute, you have a relative max, and then negative to positive here at 2, so you have a relative min. Okay? So, let's write that. So, going up here, that means we have a relative max at 1 and 2/5. How did we find the 2/5? The 2/5 is the same thing as f of 1, meaning you plugged 1 into your original function. When you plug 1 into your original function, notice that this part just gives you 2/5, and then you have 1 minus 1 raised to the 2/5, which is 0. Okay? Now, we're going to find, or we know, that we're going to have a relative min at 2, and it's going to be negative 1/5. That's going to be equal to f of 2. You should take 2, substitute that in here. You get 4/5 minus 2 minus 1. 2 minus 1 is 1. 1 raised to the 2/5 is 1. So that gives us 2/5, or not 2/5, 4/5 minus 1. 4/5 minus 1 would give you negative 1/5. Okay, write it out if you need to. Now, that's part B. Part C, I'll draw a line here. Part C, we need to find if we have points of inflection. Well, that means we need to find our second derivative. So remember, our first derivative was equal to this function. So now we need to differentiate this function. The derivative of 2/5 is 0. So now we differentiate this portion, which means you'll have negative 2/5 times negative 3/5, because you bring that down, times x minus 1 raised to the negative 3/5 minus 1. Write it down if you need to. That will give us 6 over 25 times x minus 1 raised to the negative 8 over 5. That's the exponent here. Okay? Or we can rewrite that as negatives, or not negative, we can rewrite that as 6 divided by x minus 1, that quantity raised to the 8/5. Our 25 doesn't disappear, so we make sure to write that. That's our second derivative. Notice that our second derivative is never 0, but it is undefined at x equals 1. It's undefined at x equals 1 here. But what that means is we don't have a point of inflection, right? We don't have a point of inflection here. So not a point of inflection. Okay? Now, the domain for part D, the domain of f of x, notice that f of x is equal to 2x over 5 minus x minus 1 to the 2/5. The domain of that is all real numbers. Is all real numbers. So that means there is no, or there are no. Let's give us a little more room. There are no singular points. Now, in part E, that means we need to examine the behavior of your function near infinity and negative infinity. Okay, so we are examining the limit as x approaches negative infinity of 2x over 5 minus x minus 1 raised to the 2/5. And as x approaches negative infinity, we're going to get negative infinity here. Because these numbers are going to still, oops, I didn't mean to write that. These numbers are still going to get larger and larger, or smaller and smaller negative. Okay, so we can draw this portion of the graph. We know that we're going to get negative infinity here. Well, we know our function has to come back down. And then we know it has to go back up here. So that kind of tells us what the behavior is going to be as x approaches infinity, but let's write it out for sure. The limit of f of x as x approaches infinity is equal to the limit as x approaches infinity of 2x over 5 minus the quantity x minus 1 raised to the 2/5. And as x gets larger and larger, these numbers over here get larger and larger, and this dominates. So we get infinity. Okay, and that's it. This is our graph. That's our sketch. Okay, make sure you go through the homework problems. This is a lot of information, I know, but the more problems you do, the better you'll get at it. Have fun.